Okay, good. So the next point on our agenda is actually the challenges. I guess I have a couple of more minutes, so than I had originally planned for. So I will present a few more slides than I had originally planned. Give me 1 second. Okay. So as part of the workshop, we had this challenge on visual localization in changing conditions. So what we essentially wanted to figure out is how robust are our algorithms when we capture a map under one condition and then try to relocalize under different conditions. More precisely, we had 3 challenges. So one was the autonomous vehicle challenge, where we provided 3 datasets: the extended CMU seasons dataset, the robot car seasons dataset, and the SILDa dataset. And I'll talk a bit about the datasets in the end, where you actually have images captured from something like a vehicle, where you have image sequences that you could actually use for this. We are going to have 2 talks here. The first one is the first place in the challenge by Martin Hummenberger and others, who present their work on robust image retrieval-based visual localization using capture. And the second place is by Unaga, Lindenberger, Celepidis, and Salin on 6DOF pose refinement via sparse to dense feature metric optimization. The second challenge was on handheld devices. So rather than having sequences captured from a vehicle that moves on the ground, we actually had images captured with with mobile phones that can undergo a complete 6DOF motion, and where we actually have only individual images. So here we have 2 datasets: the Aachen day-night dataset and the InLoc Dataset. And here we are again going to have 2 talks. The first one is by Zarlin and others on superglue learning feature matching with graph neural networks. I think this is actually a CVPR paper this year. And the second one is by Fan and others on visual localization using semantic segmentation depth prediction. And the third challenge was the local feature challenge, which is only done on one dataset, Aachen day-night, where we're actually only using the nighttime images. And the idea here is that we wanted to isolate the impact of different feature detectors and descriptors on localization performance. So what we do is we provide source code for a simple localization pipeline, which does feature matching between a predefined set of images, then builds one local 3D model for each test image and tries to localize that model against this local model. And for this, we actually have code online if you want to use it. Here we have one winner, which is Zalin and others, Superglue, learning feature matching with graph neural networks. And we actually have 2 second places, which ended up is identical scores, Lu and others, based on 2 papers, learning local features of accurate shape and localization, and learning 2-view correspondences in geometry using auto-aware network. And the second one is Revo and others, R2D2 repeatable and reliable detector and descriptor. I think this paper was presented last year at NIMS. The way that we handled the challenges was we have this benchmark server at visuallocalization.net, where you upload a text file with image names and the 6DOF poses that you computed, and the server does the evaluation. So the ground truth poses are actually not public. So you just submit the results on that website, and then typically a few minutes later you get results. As an additional rule, we had the rule that there should be either paper or archive technical report that had to be available shortly after the submission deadline, so that we could verify what was done. In terms of the evaluation, so for each data set, we have multiple conditions. So what you see here is the Aachen day-night data set, and the first column is essentially the percentage of images localized within 25 centimeters and 2 degrees of the ground truth. And then the second column is percentage of images localized within half a meter and 5 degrees, and so on and so on. So we get multiple numbers per method and per data set. And the way that we combine them is we consider this as we use the Shuxue method, which was originally designed for a voting problem where voters can vote for candidates. And essentially each voter produces a preference for candidates, which is a list where you say, I would prefer this candidate over this candidate over this candidate, and so on and so on. And then this method tries to find a global ranking that preserves those relative rankings. In our case, the voters are the different conditions. So for example, night at the highest precision threshold that we're looking at, and the candidates are the methods. So we use this method to get a global ranking. For the data sets that we used, we have the Aachen night dataset, which is a 3D model built using daytime images, and we query with relatively high quality nighttime. The model was built using daytime images. We query with relative high quality nighttime images, which were taken with a mobile phone and software HDR. We have the extended CMU seasons dataset, which is based on a dataset that CMU captured 9 years ago by now, where we have seasonal changes and a bit of illumination changes, and we again build a model under one condition and then provide test images taken under different conditions of different seasons. There is the robot car seasons dataset, which is based on a paper by Will Maddern and others from 3 years ago, where they captured Oxford over a full year. And we use one of those runs a day to build a reference model, then have runs at different weather conditions. So we have rain, different illumination conditions, dawn and dusk, and so on, and also nighttime images. And this one is much more challenging than CMU and Aachen in the sense of there's motion blur in the images, especially at night. We have the SILDa dataset, which was captured by Scape Technologies and the Imperial College of London by essentially traversing the same block in London under different conditions using a wide field of view camera. And finally, we have the InLoc dataset, which is an indoor dataset which captures 2 floors of a university building. That's the University of Washington in, don't fully remember where. So it's an existing data set, and which provides panoramas and depths that are registered onto a floor plan, and we captured additional test images a year or so later. So, and again, you have illumination changes, you have changes in the scene. So it's a pretty hard data set, especially since some of the regions are very weakly textured. I want to thank the sponsors that helped us make the challenges work. So that's Apple, Facebook Reality Labs, Microsoft, and Niantic. So big thanks to all of our sponsors. And we have one announcement to make, which is that we're going to run the challenges again at ECV this year. So we're currently planning for a submission deadline around August 15th, and the workshop will be taking place on August 28th. And since ECV is virtual, the workshop will also be virtual. If you want to know more, you can have a look at the workshop website. And I will also put the slides up on the workshop website later. Okay, that being said, we can start with the talk for the first challenge. That would be Martin Hummenberger presenting the winner of the Autonomous Driving Challenge. Martin, the floor is yours.
Hello, everybody. Can you hear me?
Yep.
Good, then let me share the screen. Can you see my screen as well?
Yes.
Looks good. Okay, so thanks a lot, Torsten. So hello, everybody. My name is Martin Hummelberger. I'm with Naval Labs Europe, and I will present our work for this year's Visual Localization Challenge, which is entitled Robust Image Retrieval-Based Visual Localization Using Capture. This is joint work with a couple of colleagues from Naval Labs. In Italy, Johan, Nicolas, Julien, Jérôme, Philippe, Noé, César, Vincent, and Gabriela. So Naval Labs is an ambient intelligence technology company owned by Naval Corporation, which is Korea's leading internet content service company. Naval Labs Europe is based in Grenoble and is the biggest industrial research lab in artificial intelligence in France. In the next 10 minutes, I will first briefly talk about the concept and methods of visual localization. I will introduce our method. In detail, I will present our image retrieval and local feature extraction methods. I will present the achieved results. And finally, I will introduce our new data format and computation pipeline, which we call Capture. Visual localization, as you know, addresses the problem of estimating the position of the camera using images. In comparison to GPS, the estimated position can be more accurate, and we can directly compute the camera's orientation. And furthermore, as we just saw by the impressive demo of Victor, it also works indoors. A lot of great work has been done in the last years in the field of visual localization in order to overcome challenges such as illumination changes, viewpoint changes, or any other changes between the reference and the query images. These slides should provide a brief overview about very relevant work in the last years. We believe that especially image retrieval-based methods are very interesting because they offer an interesting opportunity to combine data-driven and geometry-based approaches. As a result of that, they provide the basis for our method. So following the traditional pipeline, our method consists of two main parts. The first, mapping part, computes a 3D representation of the environment, and the localization part computes the precise position of the camera in this map. And we implemented all these steps in our processing pipeline, which we called Capture. For mapping, we first select pairs of similar reference images using our global image features AP-GEM. Then we compute pixel-wise correspondences using our local feature extractor R2D2. And finally, we use CallMap to compute the 3D reconstruction. For localization, given a query image, we first retrieve the 20 most similar reference images using, again, AP-GEM. Then, given these pairs, we compute pixel-wise correspondences using R2D2. And finally, given the resulting 2D, 3D correspondences, we use CallMap to compute the 3D pose of the query image. Let me now explain more in detail let me now give you more details about the used global and local features. And I will start with AP-GEM. So AP-GEM stands for Average Precision Generalized Mean Pooling. And the method was published at ICCV 2019. And we have models and code available on our website. For deep image retrieval, usually a CNN is used to extract a feature map that is aggregated into a compact fixed length representation by a global aggregation layer. And this representation is first projected with a fully connected layer and then L2 normalized, so images can be efficiently compared using the dot product. The motivation of this work is that state-of-the-art methods in deep image retrieval rely on loss functions that minimize a proxy instead of the true metric used during model evaluation. And we argue that optimizing for the true metric leads to significantly better results. Thus, instead of using the triplet loss, which is not guaranteed to be aligned with the ranking metric, we propose to directly minimize the average position for a large number of images. And for more details about AP-GEM, I would like to refer to our paper. As mentioned before, for local pixel correspondence analysis, we use our local feature method R2D2. It was published in NeurIPS 2019, and again, code as well as models are available online. As you know, the one quality criteria of key points is repeatability. It is often used to find good key points, and it tells us how well a key point can be detected at the same location across different viewpoints. R2D2 revisits the question of what is a good key point by introducing reliability as additional criteria for feature extraction. Reliability essentially tells us how well a key point is suited for the task of matching. Here's the architecture that we propose to estimate repeatability and reliability densely at each pixel. At the end, we only keep locations that are both reliable and repeatable. And here's how we train the network using image pairs with ground truth pixel correspondences. For repeatability, we minimize the cosine similarity between detector responses in two corresponding patches. And for the joint reliability and descriptor loss, we maximize the average precision computed for each query patch, weighted by the estimated patch reliability. For more details about the losses and the training procedure, please again refer to our paper. Let's now talk about how our image retrieval-based method performs on the visual localization datasets. Since we are looking for a robust method that performs well under different circumstances, we did not change the method, training data, or any parameters across the datasets. Let me start with the datasets from the autonomous driving task. The final consolidated ranking can be found on the website, and here I will use the official benchmark for comparison. So on robot car seasons, we rank first out of 47, and our method performs particularly well on nighttime. On extended CMU, we rank 4th out of 30, and on SILDa, we rank 3rd out of 10. For all datasets, whenever possible, we utilized image sequences and the multi-camera rig configuration to interpolate and to complete missing poses. We also ran our method on the datasets for the handheld localization challenge. So on Aachen day night, we rank 4th out of 55. And on InLoc, we rank 28th out of 35. The results on InLoc clearly show the limitations of image retrieval in such indoor scenes. And note that we did not change our workflow, which means that we did not follow the proposed InLoc localization pipeline. Considering our experiments with the presented datasets, we can summarize the following findings. Most importantly, using a list-wise loss is beneficial for the task of visual localization because it enables to train the networks directly for the task at hand, using a large amount of samples in the loss function and without the need of hard negative mining. This is one reason why R2D2 and APGEM perform well. Then structure-based methods provide a good way of combining machine learning with geometry, which also increases robustness. And we think that there's more potential in utilizing image sequences and multi-camera rigs. And of course, situations where the environment dramatically changed, for example, caused by snow, still are an interesting challenge for image retrieval. Finally, let me introduce capture. So during our work on visual localization, we often face the challenge that many datasets are provided in different formats. This does not only mean that data importers and exporters need to be adapted, it almost always means that coordinate systems or camera parameters need to be transformed as well. Furthermore, if you want to use a combination of multiple methods in a single pipeline, a lot of data conversion is needed. In addition, even if there are great tools like OpenMVG, as we heard yesterday, or CallMap available, the provided data formats did not include everything we needed. For example, we wanted to use Wi-Fi data or other sensor data. And that's why we created Capture, and we hope that it will facilitate research and development in visual localization, structure for motion, VSLAM, but also in sensor fusion in the future. So now let me give you more details about Capture. So Capture is a versatile and extensible format for structure for motion and other data. It's a set of converters between many popular formats. It's a set of tools, for example, for merging data sets or for evaluation and visualization of localization results. It also contains a Python library, which can be used to load, save, and manipulate captured data. And this this library can be used to create new converters and custom processing pipelines. As an example, we will provide a mapping and localization pipeline based on CallMap, where you can either use CallMap SIFT features or you can use your own custom features and matches. And more functions will follow, which will complement existing tools. Capture will be released soon on GitHub under the BSD license. And we also plan to release a rich set of capture data from many popular datasets. And of course, we know that researchers who already work on structure for motion or VSLAM or visual localization might already have implemented their own toolset. But on the one hand, we hope that capture will still be interesting for researchers already active in the field. And on the other hand, we hope that it will actually attract new researchers. So this brings me to the conclusion. I presented our robust image retrieval-based visual localization method, which utilizes global features APGEM and local features R2D2. Using a single method, we report very good results on a set of quite different data sets. And I introduced capture, a versatile data format, to facilitate research and processing in visual localization structure for motion. We really hope that this will have a positive impact on the community to provide even more data sets and algorithms. And finally, I really would like to thank the organizers of this great workshop and the interesting challenges. This really is an inspiration for many researchers in the field. This concludes my talk, and thanks a lot for your attention.
Thank you very much. Just to bridge a bit of the time before there are questions on YouTube. I very much like the capture format. Do you plan to provide pre-trained data sets, so to speak? So will you convert like the data sets from the challenge into that format?
Yes, exactly. So that's, sorry, I need to modify. I don't see myself. Anyway, yes, thanks for this question. That's one of the main reasons actually we decided to release this format open source, that basically ideally all public visual localization datasets should be available in the same format, and that it's really easy to process them. And in particular, to your question, yes, the plan is to actually release all the datasets where we have like the rights for in the same format, that you just need to basically download this Python library and you're ready to go. Yeah,
let's talk a bit about this after the workshop, because we can see whether we can host it together with the official datasets if there's interest from your side.
Of course, that's very much.
And if we're not running out of disk space. Okay, so by now we have a couple of questions online. So what is the real-time performance of R2D2?
So R2D2 is, we extract it on multiple scales. And if you extract like all scales, which means, I don't know, 4 or 5, 6 scales, then on a good GPU, it's probably between 2 and 3 seconds per image. But if you reduce it, so in the code you can see that you can reduce the image size, and you can get it down to less than a second.
Any did you, as a follow-up question, did you try to play with the architecture, like do model compression, things like this, to try to see whether you can push the limit there?
So in terms of making it smaller and faster, we didn't do a lot yet, to be honest. We're currently working on, I mean, we are constantly running experiments with slightly modified architectures, training data, and we actually also achieved even better results than we could submit to the challenge at the end. But nothing was really yet consistent across all the data sets. So we decided to wait till we are really sure about this. But no, we haven't done anything in particular to make it faster or smaller.
A question from YouTube. What approaches do you think could help improving indoor image retrieval performance?
Yeah, that's a good question. And that's actually a question we ask ourselves a lot. Initial experiments we did by combining multiple global features were actually quite promising. Again, nothing really consistently working across all the data sets was found yet, but we plan to investigate in this direction, to combine multiple global features in a way that they like that the combination of many is better than each individual. If we would only like to stay with image retrieval based methods, right? I mean, there are other ways of improving this with like including more geometry, for example.
Thank you very much. Yeah, thank you very much for the very interesting and nice talk.
Thank you.
Oh, wait, there's actually 2 more questions. So maybe we do one of them. Is the weak performance in global descriptors for indoor cases mainly due to the fact that they are usually trained with outdoor data? I think that's actually an interesting question.
Yeah, I mean that's what we assume as well. I mean, there's in indoor you always have also the problem that like slight orientation changes might completely change the appearance of the image. But for example, APGEM is trained on Google landmarks, and yeah, so that certainly is a problem. Yeah. But we will actually further investigate this.
Great. Yeah, thank you very much again.
Thank you.
For the next talk, I think we're actually going to have 3 speakers: Ayak, Kumar, Philip, and Nikolaos. Yeah, the floor is yours.
Hello, thank you. Let me just start my screen. Yeah, welcome everyone. I'm going to present our work on 6D pose refinement via sparse-to-dense feature metric optimization. This work was in collaboration with Philip, Nicholas, and Paul, and we are master students at ETH. Our approach for this challenge was to look at the current approaches, find their limitations, and try to improve on top of it. For example, it's well known that sparse key point matching is not repeatable. So rather than that, we use the sparse to dense feature matching, which was proposed recently. Another problem with the learned descriptor and learned features is that they are not well localized in the pixel space. So we are trying to do pixel level feature metric optimization, which can improve localization errors without any additional training of the features. At the end, we will present our results on robot car and CMU. Let's start with the sparse feature matching. It's a well-known approach where we detect key points in reference and query images, and we try to match them. However, the problem with this approach is when we have a large illumination changes, for example, here from day to night. Even well-known descriptors like superpoint and hypercolumn, they are not able to get good number of inliers to find the good pose. Another problem which is with most of the learned descriptor is that they are not well localized in the pixel space. For example, as you can see here in the top right image, we have reference key points, detected key points, and in the bottom right image, we have the matched query points. And if you can qualitatively see, the points are not matching well. The small pixel error, however, can result in large error in the pose estimate, as we can see in the left column. So recently, Germain et al. Proposed an approach called sparse to dense matching. Here, you detect points only in one image, for example, reference image, and you pass it through off-the-shelf trained image retrieval network, and you get your features. However, for query image, we don't do any detection. We just pass it through the network and we get the dense descriptors. Once we have the sparse and dense descriptors, we do the matching. Basically, we do the correlation map and we find the corresponding match. However, the same problem with this approach is that it's not well localized. The reason is that the output of the network would not be at the same resolution as the image. So as we can see here, the points in the left, where we have well localized corner points is the reference image, but in the query image, we don't have well localized points. That's what we are focusing on. We will try to improve that with this approach. Also, recently there has been some approaches which use feature metric based optimization in different applications like multi-weather relocalization or bundle adjustment. The common thing between these approaches is that they use multi-scale features to apply this feature metric optimization. We observe that in our network also we have multi-scale features. For example, if we take S2DHM network and pass the query image, our early layers are very sharp and our deeper layers are very smooth. So the smooth layer can maybe help us get the higher radius of convergence in optimization, and this sharper layer will help us achieve the pixel level accuracy. We observe the same thing when we look at the correlation map. For example, here we have a reference image, query image, detected key points, and correlation map. Now, if we zoom in, we can see that our correlation map have a gradient. And if we are a bit off from this gradient, for example, these blue points, then we can use the optimization to guide that point to the optimum. And based on these ideas, we define a method called feature metric based PNP optimization. Here I will detail it. So we have a 3D structure points, for example, capital P, and we have a projected reference point, small p. Using this, we can already define our reference feature map from the reference feature map FR. However, for query feature map, we'll have to start with some initial estimate of our query pose. So we start with some initial estimate, we project 3D point on the query image, and we find corresponding query features. Once we have reference and query features, we define the error between them as a feature metric error. Our optimization will try to minimize this error. We are here using Levenberg-Marquardt methods with the squared error loss formulation and iterative optimization. However, interesting thing to note is that this TQ cannot be arbitrary pose. Because we have a limited radius of convergence, we need some good initial estimate. So we initialize T with the PNP plus Ranzai. Now let's look at this in the qualitative manner. So first, main benefit of working in feature space rather than intensity or pixel space is that we can use optimization across changing condition. So for example, from day reference, we can do optimization on night query as well. Here, as we can see, if we start even with some wrong pose, our optimization guide all the points to their corresponding matches. Even as we can see, point movement is also pretty large, which shows that we have a good enough radius of convergence. Another way also we need to look if our feature metric error is actually decreasing. So for example, here we show the feature metric error heat map for the points marked in the colored boxes. We can see most of the points are going towards their minima, except for some points which are in ambiguous regions, like for example, black sky or the tree. Also, however, with the small movement in the key points, we can have a very large movement in camera, which was our first point, that even with the small movements, small improvements in the key point location, we can have a large improvement in localization, as we can see here in the right image. Next, we can see that after the optimization on the right image, after the optimization, our key points are on the right location than before optimization. Another metric to look at is the number of inliers. So we compare the number of inliers before optimization and after optimization, and we get more inliers in cases when we apply optimization rather than using the original PNP plus Ranzai pose. Now let's look at some quantitative results. So we use this method on robot car dataset with S2DHM features. First, we use off-the-shelf given S2DHM features with their layers, and we apply our feature metric PNP on top of it. Here we find improvement in most of the threshold except for some threshold in daytime images. However, However, when we use the combinations of different layers, as in earlier layers and deeper layers, in those cases we find improvement in all the cases, and this improvement is very strong in the lower threshold, and we have a medium decrease, medium increase in the some medium thresholds. Nevertheless, this approach seems to work for all the threshold in the robot car dataset. However, for extended CMU, the story is a bit different. Here, our feature metric PNP didn't improve the results, but we used the different hypercolumns than what S2DHM paper proposed, and it needs a bit more investigation. Let's look at the post change. So after the optimization, our post should change a bit. So here we show that after the optimization, our robot car post change around 0.45 meter and extended CMU change around 0.2 meter. This explains the performance increase in the lower threshold than the larger threshold because it's a local optimization and we can't converge if the original pose is very far from the actual pose. So in summary, we present the feature metric error optimization based on sparse to dense feature matching. We use the idea that features have a gradient, and you can use this gradient to do the optimization and improve your current localization without any additional training. This approach works very well on at least robot car, and it performs state-of-the-art on night-all sequence. We will have our code and report on archive in next days. Thank you for listening.
Thank you very much for the nice talk. I think we have time for one or two questions, and so maybe I started off with so here you're doing the
Yes.
sparse to dense matching, right? Can you think of a way of taking the lessons that you learned and lead for training better sparse to sparse features?
Yes, so this is where the next part will come in. Basically, we can there are methods, there's BNet, right, and also the GNet loss. That's what they do basically. They use this, you can use the loss itself to guide your feature training, and this will in response will generate smooth gradients and smooth features, which can be used for sparse to sparse matching as well, but plus you can optimize on top of it because they are smooth.
Yeah, that sounds good. Let's see whether there's still one question on YouTube. Do the other organizers have a question? So there's one question on YouTube. Is it possible to directly optimize the camera pose?
We are optimizing camera pose, but we have to define some kind of metric for it, right? So here we use a feature metric error, and we don't have any ground truth camera pose. So no, we just use the feature metric error as a surrogate metric to optimize for our camera pose.
Okay, thanks. Yeah, then thank you very much for the great talk.
Thank you.
And for participating and for submitting.
Yep.
Actually, there's one short question. Maybe you can answer this. What might be the reason why the proposed approach does not perform well on the CMU dataset?
Multiple reasons, I guess, but one that we thought of was that we used a different layers than what S2DHM originally proposed, and we didn't tune anything on the S2DHM approach. Like we didn't tune our optimizer at all. So while working with it more, it should become much better, I guess.
And maybe one final question in terms of runtime overhead. How much does your optimization introduce in terms of computational?
Optimization is fast because it only depends on how many points you have, how many inliers you have. But it might take a bit more time in terms of, because you'll have to store the dense descriptor to get the gradients, right? So it might take some more memory, but in terms of runtime, it's pretty fast.
Okay, Great. Yeah, thank you very much again.
Thank you.
Our next speaker is Paul Edouard, who will present the first place in Local Feature Challenge. The floor is yours.
Thank you. Let me share my screen. All right. Can you see my full slide?
Yes.
Perfect. Then let's start. So hi, everyone. My name is Paul Edouard Solin. I am a PhD student at ETH Zurich, supervised by Mark Polyphase. And I will now present our winning entry to the Local Feature Challenge based on our paper, Superglue, Learning Feature Matching with Graph Neural Networks. This work was carried out at Magic Leap as my master's thesis in collaboration with Daniel Detone, Tomasz Malisiewicz, and Andrew Rabinovich. So Superglue is a deep neural network that performs feature matching. It reached the first place in actual 2 visual localization challenges. One is the Local Feature Challenge, which is specifically evaluating image matching for day-night localization, and that will be the topic of this talk. And the other is the challenge for handheld devices, which evaluates a full indoor-outdoor localization pipeline. So I will describe our pipeline in a later talk scheduled in about 25 minutes. And for now, let's see how Superglue works. So Superglue combines the best of 2 worlds: deep learning with graph neural networks and classical optimization with optimal transport. It is a deep middle end that estimates matches between local features in 2 images while rejecting unmatched points. As you can see here, it can successfully match image pairs with extreme baseline in real time. And this results in state-of-the-art pose estimation with both classical and learned features like superpoint. So let's first look at the typical 2-view matching pipeline. First, key points are extracted, actually detected in each image independently, and the corresponding descriptors are extracted. So this can be done with classical methods like SIFT or learned ones like superpoint. These features are almost always matched by lookup of nearest neighbors in the descriptor space, which is naive and often prone to failure. So then incorrect matches are filtered with heuristics like the ratio test, or recently with deep network classifiers that operate on sets. And finally, a relative pose is computed by a robust estimator like RANSAC. So in contrast to these, our Superglue jointly performs context aggregation, feature matching, and filtering in a single unified architecture trained end-to-end. And the ability to leverage context, particularly global context, is critical in situations that exhibit little texture or extreme self-similarities. So in this checkerboard example, local descriptors are really not sufficient to correctly match most corners, while knowledge of nearby and distinctive objects like this book can disambiguate all difficult corners. So our deep matcher takes as input local features extracted from 2 images, and each composed of key point coordinates, confidence, and a visual descriptor. Each key point can be matched at most once, and some will be unmatched due to occlusion and failure of a detector. So we seek to output a soft partial assignment matrix. Superglue is composed of 2 blocks. First, a graph neural network processes the appearances and positions with powerful attention mechanisms. It encodes contextual cues and priors into deep features, and it reasons about the underlying 3D scene. These deep features define the cost of a partial assignment problem, which is solved in a differentiable manner. This produces the desired partial assignment, enforcing thus the domain-specific constraints. So let's look at the architecture in more details. We first combine the local visual appearance and the position into an initial representation using a multi-layer perceptron, this MLP here. For each key point, this representation is iteratively updated using information from all the key points either in the same image or in the other image. And we can actually see the two sets of key points as nodes of a complete graph with two types of edges, what we call self-edges and cross-edges. So we thus use a kind of graph neural network called a message passing neural network. At each layer, the state of each key point, its deep representation, is updated using a message computed from the self or the cross edges, depending on the layers. So for a given layer, the aggregation along these edges is performed using self or cross attention. And this is akin to a soft database retrieval of values corresponding to entries with keys similar to a given query. And it's implemented as a simple weighted average of the values, with the weights being the similarity between the query and the key. And the queries, the keys, and the values are computed from the current states of the key points via linear projection. So since the state we've seen encodes both the appearance and the position, a key point, here tile, can query its spatial neighbors that are nearby, self-similarities, or other cell-in key points anywhere in the image. So self-attention, we've seen aggregates information from key points in the same image. It can, for example, attend to distinctive key points to disambiguate self-similarities. On the other hand, cross-attention enables inter-image communication, attending, for example, to candidate matches. Together, they define a soft graph that is data-dependent, sparse, and interpretable. So the final states are called matching descriptors after a few attention layers, and the dot product defines a score matrix representing the affinity between key points in the two images. And because of occlusion noise, some key points, of course, cannot be matched. So we add a dustbin by augmenting the score matrix with a new row and a new column with constant value, what we call the dustbin score, Z. And the score matrix is the cost of an assignment problem solved with a synchron algorithm, which iteratively normalizes along the rows and the columns, and we get a soft partial assignment from which correspondences can be extracted. And we train that end-to-end in a supervised manner by simply maximizing the likelihood of ground truth correspondences, which we can get from ground truth poses and depth maps. So we trained first a superglue on indoor scenes with superpoint local features, and our deep network consistently predicts more correct matches in green here and fewer mismatches in red than existing classical and learned approaches. Interestingly, we also train another superglue for outdoor scenes using structure from motion. And we observe the same striking superiority to classical here and to learned baselines. So in our paper, we evaluate relative pose estimation with different local features, both SIFT in blue and superpoint in red. And we see that superglue consistently yields large improvements over classical heuristics and recent deep networks for both indoor and outdoor environments. So when it comes to the local feature challenge, it runs on the Aachen day-night dataset. The first step is to triangulate a 3D model with the daytime images. Here we use superpoint features, and we see that superglue yields a denser model than the vanilla nearest neighbor matcher, with overall 10% more observation per 3D point. And this difference is particularly striking in areas that have many self-similarities. We can, for example, look at this brick wall. And here we see that superglue matches all key points well at both day and night times, which requires the aggregation of a large context that superglue has. For the localization task, superpoint originally lags behind new learned features like D2net or R2D2, that's superpoint. But superglue provides a big boost of performance and makes superpoint competitive. It's hard to say whether it's truly better than the other challenge entries, given that the benchmark is a bit saturated and the ground truth pose is inaccurate. But superpoint plus superglue reaches such performance with 2 to 10 times fewer key points than other approaches. And this is due mostly to the higher repeatability of superpoint for corners, like windows and tiles, which are prevalent in man-made environments. So that results in a smaller 3D model and a lower memory footprint. If you want to learn more about localization with superglue, do not miss the second part of this talk, which will focus on how to integrate superglue into a complete pipeline for indoors and outdoors. We'll see practical tips and why superglue works. That starts in about 15 minutes. If you have specific questions, you can attend the 2 Q&A sessions on Wednesday. And lastly, superglue also won the image matching challenge this year, and I'll present our winning entry on Friday morning during the other workshop. So that's pretty much it. In the meantime, you can check out the paper, code, and slides on our website, pierre.com/superglue. And if you have any questions, I'm happy to answer them. Thank you.
Thank you very much. It was a very interesting talk, and thanks for pointing out that the Aachen data, the local feature benchmark is a bit saturated. We'll have an updated version of this with what we believe are better ground truth poses at EC. So
yeah, I'm very excited about that.
And well, let's see where this goes. There's a couple of questions on the chat. I have one question. So I think it goes back to the 90s or so, the idea of using neighboring features to disambiguate matches.
Yep.
Did you compare against any of those classical things? So there's a lot of literature on this also in image retrieval for fast spatial matching and so on.
Yes, there's some literature, mostly from the late 2000s, something like that. Mm-hmm. Nothing really recent and really kind of first easy to use and easy to evaluate, and second, nothing that is widely used. So we've seen GMS in the past years that kind of helps when we have very dense features. So we have some evaluation against that in the paper, and GMS is really not competitive with superglue. Yeah. But
GMS reinvents something that was reinvented in the 90s, that was reinvented in the late 2000s, that was actually invented in the 90s.
Yeah, I guess these are very old ideas, and it's interesting that we still don't have an easy-to-use handcrafted method that can actually leverage these cues.
Yeah. Okay, thanks. Let's go through a couple of questions from the YouTube chat. One was, by using GNN, self and cross attention is required, but it looks like using CNN instead of GNN is also possible to do a similar thing. Do you think GNN is better in this problem?
So we use GNN, and for the context aggregation, we use attention. There are other methods to compute this message that we've seen previously, and these could be, for example, building a k-nearest neighbor graph, something like that. But we basically need a way to define some graph. And in our case, attention allows to learn this graph in a soft manner, which is we don't make any assumption on the structure of the problem, and I think that helps a lot.
Okay, maybe one more question. Do you consider all possible pairs of features when building the graph? If not, how do you select which features to connect in the graph for both self and cross attention?
That's a very good question. So we indeed use all the features. We assume a fully connected graph. And at each step, we either run the self edges or the cross edges. But basically, the union of the self and the cross edges define a complete graph. So that's indeed a bit expensive, and that's a bit memory intensive. So that's one of the limitations of a current approach. And I think there's a lot of potential to improve on that, using sparse attention, using sampling, so that we don't need to compute all these relationships. Because especially in the later layers, only a few key points are interesting to the network. So there's a lot of waste in compute. That's a very good question, and I think there's a lot of potential for that.
Great. Maybe one final short question. Do the weight of superpoints also get updated when you train superglue?
So in most of our experiments, we kept superpoint frozen so as to enable a better comparison with previous works. But we actually have some evaluation in our paper where we backpropagate through the descriptors of superpoint. And so we do that on ScanNet, on the indoor model, and we actually see some improvements by optimizing everything jointly. these are very initial experiments, and I think there's a lot of optimization to be done there to better train them end to end. But that at least everything is differentiable, so that's theoretically possible.
Okay, great. Yeah, thank you very much for the great talk.
Great, thank you for these questions.
And there's a lot more questions on the YouTube chat, so if you have some time, feel free to answer them.
I'll do a pass. Thank you.
On next talk is by Sichin. I think you wanted to.
Yes. So, hi everyone. So this is Jing, and first of all, I'd like to thank the organizers for having this fantastic workshop. Now I have recorded a video for this presentation. So in case of any network instability, and we will meet you later in the QA session. Okay. Yeah. Thank you. So if it doesn't work for you, SLFit, which jointly learns local feature detections and local feature descriptions. We use its original model, which is trained on GL3D dataset, and select up to 10K key points and perform only single-scale detection. We have observed that the learned key points or dense feature extraction frameworks are in particular helpful regarding large illumination change. However, inconsistent conclusions can be drawn in the image matching workshop regarding large perspective change, which indicates that there still exists potential performance gap between handcrafted key points and learned key points. After local feature extraction, we apply OANet, which is a learning-based outlier rejection method for feature matching. OANet is separately trained on FTC dataset, consumes a set of putative matches that survive the mutual check, and rejects those matches whose confidence scores predicted from the network are lower than 0. As a result, we found that a learned outlier rejection is consistently beneficial for different learned features, such as context desk or ASL fit. As shown by superglue, more potential from an end-to-end feature matching method can be expected. Next, I will briefly go through the methodology of ASL fit. In this paper, first, we address the importance of estimating accurate local shape of key points for improving the geometric invariance. More specifically, we resort to deformable convolutional networks to densely predict and apply local shape transformation. Furthermore, we compare different parameterization of deformation and study what deformation is useful for learning invariant features. Next, we address the importance of key point localization accuracy for solving the geometry. More specifically, we adopt the hypercolumn representation and perform a multi-level detection to recover the low-level geometric structures and restore the spatial resolution accuracy. Meanwhile, we compare different network designs to explore the efficient way for feature fusion. We base our methods on D2Net framework and apply aforementioned modifications, namely deformable convolutional networks and multi-level detection. We optimize the implementation with other minor changes, such as a peakness measurement and an adaptation of advanced loss formulation. We thoroughly do evaluation studies and extensively carry out experiments on image matching tasks. Structure from motion, image retrieval, visual localization, and dense reconstruction tasks. The empirical results show that our methods have delivered remarkable improvements upon the state of the art. Thank you for your attention.
Hi, this is Jiahui from Tsinghua University. I will give a brief introduction to OANet, our learning-based outlier rejection method presented in last year's ICCV. Here we focuses on the two-view geometry estimation problem, which is Given a pair of images, we estimate the essential or fundamental matrix. We construct putative matches by using SIFT or other learned local features. Then, to obtain accurate relative post-estimation results, we have to find these outliers. In this paper, we'd like to use a network to distinguish the outliers and inliers. One of the challenge is how to capture the local context for the putative matches. This is non-trivial because they are sparse and unordered, and our solution is using learned clusters to capture the local context. Here is an overview of our architecture. The input of the network is image coordinates of putative matches, and the output are inline probabilities and EF matrix. We use a unit-style architecture. The core of the network is the differentiable pooling and unpooling operation. The differentiable pooling layer clusters input nodes to a cursor representation by learning a soft assign matrix. Matches fall into the same cluster are learned neighbors. The network can capture local context by this clustering process. The differentiable unpooling operation can be simply seen as a transposed version of differentiable pooling layer. Besides, we show that these clusters obtained by the differentiable pooling layer are in canonical order, which means we can capture the relation between these clusters by using more powerful operations, such as fully connection layer between clusters. We extensively conduct experiments on several benchmarks. Our method can outperform previous handcrafted methods and learning-based methods. It works best when using ransack variants as post-processing. Besides, we also test the network's generalization ability on 4 different datasets, which shows our method generalize well and outperform both traditional method and learned method in these benchmarks. Thanks for your attention. You can check out our code on GitHub.
Thank you very much.
Yeah, thank you.
I think we have time for one question. If there is something from the audience. Otherwise, I have a short one. Have you thought of jointly training or ANet with ASL feed?
We haven't tried that because ONet is quite memory consuming. Also for AS feed, the input to ASL feed is like 500 by 500 images. So it's also quite high resolution for training. And we also suspect if it is useful to propagate the gradient from ONet to the local feature module. So we haven't tried that due to those limitations. But I don't know, if we have better hardware devices, we can definitely try it out. Yeah.
Okay, great. So in the interest of time, we will move to the other second place finisher for the local feature challenge. If you still have questions, please ask them on the chat. And Sichin, if you have time to answer them, that would be great. Otherwise, yeah, thank you very much for the great talk. And I give the floor to Martin, who's going to present R2D2.
So thank you. I hope everything works. So this is Martin Huenberger again, and from Naval Labs Europe, and I will present our work R2D2 now a little bit more in detail than before. R2D2 is a repeatable and reliable detector and descriptor, and this is joint work with Jérôme Revaux, Philippe Weinzäpfel, and César de Sousa. All right. First, I will present the problem we're interested in, and this is about finding pixel correspondences between images. And the classical approach is to first detect key points at scale space locations to the locally salient, or as we say, repeatable. And then for each key point, a patch is extracted and encoded into a compact descriptor. As you know, the most famous key point detector and descriptor is SIFT, and it's still widely used. And then finally, descriptors are compared between the two images. And when two descriptors are very similar, it means we have a pixel correspondence between the images. And the resulting set of pixel correspondences can be used, for instance, to recover the camera pose. In practice, however, the key point matching often fails. And we believe that one reason is that existing approaches only consider a single quality criteria when extracting key points, when that's called repeatability. And repeatability is, of course, important because it means that the key point will be detected at the same location across different viewpoints. In this work, we claim that there is one more essential quality criteria that should be taken into account, and we call it the reliability. It basically tells us if a patch is good for feature matching. This distinction between repeatability and reliability is important because patches can be repeatable without being reliable. For instance, in repetitive structures. To summarize, in this work, we would like to revisit the question, what is a good key point? Here are some examples to concretely illustrate the difference between repeatability and reliability. The first key point is obviously neither repeatable nor reliable. This one is very repeatable as there is a high corner response in the center, but it's not reliable due to the repetitive pattern. We formally measure reliability by searching for the closest key point in the descriptor space and then checking the difference compared to the original one. In this case, the nearest neighbor is almost indistinguishable from the original one. This one, on the contrary, is not repeatable since there is no salient structure at the exact key point location in the middle of the patch, but it is reliable as the most similar patch in the image is still significantly different. If you look at the boats, you can see that. And finally, here is a key point that is both repeatable and reliable, and this is exactly what we're looking for. So let me present the architecture that we propose to estimate repeatability and reliability densely at each pixel. And so at the end, we only keep locations that are both reliable and repeatable, even though we estimate it densely. As we saw, reliability depends on the key point descriptor itself. So our network also computes the descriptor at each pixel simultaneously. And here's how we train our network. We feed it with image pairs, and for each image, the network computes descriptors, reliability, and repeatability at pixel level. Each image pair is annotated with ground truth pixel correspondences. They can be either generated synthetically by applying random transformations to an image, or they can be sampled from, for example, structure from motion datasets, in which case we compute the ground truth correspondences using conventional optical flow methods. Our network is trained from scratch using two different losses. The first one for learning discriminative descriptors jointly with an estimator of the matching reliability. In detail, we maximize the average precision computed for each query patch, and we weight it by the estimated patch reliability. And the second one is for predicting repeatable locations in the image. Here in detail, we maximize the cosine similarity between the detector responses in two corresponding patches. To summarize, with R2D2, we make three main contributions. So first, we introduce the notion of key point reliability at extraction time, which we show is well complementary to repeatability. Second, we introduce two novel losses tailored to learn these confidences from scratch and without introducing any bias. And third, we demonstrate state-of-the-art results on tasks such as image matching and visual localization. Last but not least, the code is online on our GitHub. Thanks, that's it. And thanks again to the organizers for the workshop.
Thank you very much. In the interest of time, I think we have time for one question. I guess, since there were actually so many questions asked on the YouTube chat on R2D2, maybe we skip this. But maybe, so do you have any, one short question, do you have any improvements on R2D2 planned, something in the pipeline that we can look forward to?
Yes, of course. That's something we are heavily working on improvements. We are investigating multiple ideas about changing the architecture, including more or less invariances, but also using other training data, more structure for motion models. So we're investigating many directions, and we hope we can provide an update soon. And let me say one thing. So together with our data format capture, we also think about releasing some extracted features for popular data sets, which should make even a comparison to other methods easier.
Great. Yeah, looking forward to that. Thank you very much for your talk.
Thank you.
And I hand over to Paul Edouard, who will give the second part of his presentation on superglue and superpoint.
Great. Thank you, Thorsten. Let me share my screen. All right. Can you see my full slide?
Yes.
Good. Thank you. So hi, everyone. This is me again, Paul Edouard Solin. This is the second part of my talk on our deep neural network superglue for visual localization. For those that just joined, I am a PhD student at ETH Zurich, and this is our winning entry for the localization challenge for handheld devices. It is based on our paper, Superglue Learning Feature Matching with Graph Neural Networks, an oral at CVPR 2020. So in the previous talk, we covered the internals of Superglue and its performance on the local feature challenge, which specifically evaluates image matching for day-night localization. We will now see how Superglue can be integrated into a full localization pipeline and why it helped reach the first place in the challenge for indoor-outdoor handheld devices. So differently from the previous challenge, here we are not given a list of matching images. So we need to rely, for example, on image retrieval to find these relevant image pairs. Additionally, we are now evaluating both outdoor and indoor localization on the Aachen day-night and the InLoc datasets. So there is much more diversity in environments, and we need a method that can generalize well. So last year, we actually won this challenge too, using hierarchical localization, which is based on our CVPR 2019 paper shown here. And to briefly summarize it, we can use deep learning for both image retrieval and matching by predicting global descriptors and local features. So we can do this for both database and query images, and we can also build a structure from motion model for the database, so pretty standard pipeline. And then for a query image, we can retrieve some relevant database images. We can cluster them based on the visibility information in the graph of the SFM, and then we can match the local features. And finally, from the resulting 2D, 3D matches, we can estimate a pose. So the best combination at that time was using NetVLAD for the retrieval and Superpoint for the local features. This worked pretty well, but still had a number of issues. First, the retrieval is far from perfect, and it often has a low recall, so there is no relevant images in the top 20. Regarding Superpoint, its descriptors are not really scale invariant, and its context is rather limited, so the matching can easily fail. And in addition, its key points are not so pixel accurate, so they are sometimes not so well localized. And it turns out that our Superglue matcher can actually mitigate all of these issues. We'll see how. So as a reminder, Superglue is our deep neural network that performs feature matching. It combines graph neural networks and optimal transport to estimate matches between local features in two images, but also to reject unmatchable points. And we'll see now how we can mitigate the current issues of hierarchical localization. So we first have a look at the training pipeline. And our outdoor model is trained on structure from motion data using pairs of relevant images with ground truth poses and depth maps. Given some detected key points, we can compute ground truth matches and label some points as unmatchable. So we have green matches and red points that we know are not matchable. And this is used to supervise the partial assignment matrix predicted by superglue. The matches are here in the green part, and the red part corresponds to the dustbins, the unmatchable points. And this actually means that superglue can learn the context of the concept of visibility. It can understand that some regions of an image are not co-visible with the other image. How does this help? Well, imagine that now we have a difficult query image and the retrieval fails. Well, not that it fails, but the top, for example, 3 retrieved images are not really relevant. The nice thing is that superglue will not predict any match. Even though it was not trained with non-matching image pairs, it can still reject irrelevant images. That's because of a training process. So we can actually retrieve more images until superglue can find some matches. And here, image 39 is finally matched with 99% in-liar ratio. So that shows that superglue, in addition to having a very high recall, so more matches, also has a very high precision, near perfect precision. So we can actually retrieve more images without affecting the in-liar ratio, and we can basically boost the retrieval performance artificially. Similarly, we can look at another capability of superglue. As you can see here, we have 2 images with the key point locations, and there's actually already a lot of information in these key point locations. And we can even match these, these 2 windows, we can actually just from point cloud see that they're actually matching, and these are the same buildings without looking at the underlying images. And this is exactly what superglue can do when the visual descriptors are not informative anymore. It can learn to not trust them and instead rely only on the 2D point cloud. And this turns out to be very useful when there are large scale changes or many self-similarities, basically when the visual descriptors can fail. And here, so you see some patterns here, some kind of arcade, and we actually see the same here. We can recognize it in the 2D pattern, and that helps superglue to perfectly match this image and have a very nice estimated pose, while the actual original descriptors are pretty poor in this example. On different note, on a related tone, is the impact of the size of the input image. As we upsample the image, the receptive field and the context of CNNs shrinks. From here to there, we only see a small tile on the window. And as a consequence, the matching of the local descriptors is going to fail more often. But on the other hand, the key points become more accurate, especially when there is no subpixel refinement. And this helps the pose. And overall, the pose estimation when using the nearest neighbor matcher is not really improved because of a shrink of context. Superglue, however, expands the context of the descriptors to its maximum, basically the whole image. So we can now use large images and have a clear boost of performance because of more accurate key point without any loss when it comes to matching. And that's because it operates also on the 2D point cloud. Finally, one of the common concerns with learned methods is their ability to generalize. In our case, we observed high performance using a single superglue model for both indoor and outdoor. It works well despite different cameras, lenses, image sizes, aspect ratios, and doesn't require intrinsic parameters. It just works well out of the box. So our localization pipeline is as follows in the end. We match each query image to up to 50 relevant database images using superglue. Then these 2D matches are lifted to 3D using either a triangulated SFM model for Aachen or using the given 3D LiDAR scans for InLoc. Same pipeline, just two minor modifications on how we get the depth of the points. And it turns out that, as Martin cited previously, image retrieval is actually really hard indoor because all corridors and all rooms have similar doors and furnitures. So we cannot really trust the retrieval. To that end, we use some temporal consistency to boost it. So in the InLoc dataset, the queries are ordered, but they're sequentially ordered, and they belong to two floors, the first and the second. So what we do is that we have a multi-step approach where we first localize easy queries and we save the floor wherever we're localized. And we can use that to deduce the floors of the hard queries that are temporarily adjacent. Everything is automated, it's just filtering. And finally, we can use these priors to restrict the retrieval of the hard images. And this helps quite a lot for some examples. For example, this query is originally retrieved in the wrong building and in the wrong location. But when restricting it to the right building, then we actually get the right place that is retrieved. And then we can get matches with superglue. Finally, some results. Superglue provides a big boost to original hierarchical localization. The pipeline is very simple. And we don't need dense reconstruction or semantic mapping like ONAVI. As a summary, so I presented superglue, a deep neural network for feature matching, basically the power of attention and optimal transport to provide amazing matching and localization, all real-time, robust, and well generalizing. So I'd like maybe to give 3 takeaways, if the time allows, on our experience with superglue. First, it's a paradigm shift. We found that using the key point positions to find matches greatly helps. We do not simply rely on the appearances anymore. Second, when we have a big model and a lot of data, a big data set, the data distribution matters a lot. Here we train superglue on extremely hard examples and obtain very good matching in a wide range of situations. And lastly, we should look around. Graphs are literally everywhere in SLAM, and maybe with graph neural networks, we can learn useful priors and we should see what should be learned. So you can, if you want to learn more, if you have questions, you can tune in for our oral and live Q&A session on Wednesday. And you can also join the image matching workshop on Friday morning, where I'll give a talk, since superglue won the first place there. And you'll see some evaluation on superglue for 2-view pose estimation and structure for motion. So pretty different from our challengers for visual localization. And that's it. If you have questions, feel free to reach out by email or Twitter, and you can check our website for paper, code, real-time demo, and slides, of course. Thank you. And of course, I would like to also thank the organizers for these great challenges that everywhere are very fun to take part in, I think. Thank you, Torsten.
Thank you very much for the nice talk. We have a question online. Do you think, along with temporal consistency, forced explicit co-visibility while training could help more?
Sorry, could you repeat the question?
Do you think that along with temporal consistency, forced explicit co-visibility while training could help more?
Yeah. Could help more. And so I think there's the training procedure could be refined. And I don't think that we need maybe that strong supervision when we have so much consistency in the world out there, temporal consistency and 3D consistency. So it might be possible to derive new training strategies that involve maybe not having any poses or depth, but rather trying to maximize some matching metric, I think. That would be interesting to follow.
Let's see whether we have additional questions. So far you're looking at mostly at pairs of images, right?
Mm-hmm.
What happens if you go to, say, triplets or something like this?
So either triplets could be used, I think, for training or at test time. So at test time, it becomes a bit more involved because then we have a lot more matches and it's not really trivial how to handle that. But maybe triplets could actually provide a good supervision at training time. Because we could have some consistency beyond just epipolar geometry, we could actually have 3D consistency. that would be pretty useful. But at test time, I think that there sure would be a lot of things like that, kind of a learn structure for motion, but I don't foresee anything that is scalable, at least not in this paradigm of attention and so on.
Great. Yeah, thank you very much.
Great. Thank you.
And thanks for the great talk. Looking forward to the discussion phase of the superglue paper.
Yeah, great. Feel free to join, and thanks for the invitation. It's always
thank you. Thank you very much. Okay. And we have one final talk, which is the second place of the handheld localization challenge. Do you want to introduce things?
Hi, Professor Settler. Can you hear me?
Yes.
Please play back the recorded video for us. Thank you.
Will do.
Hi, everyone. Today, I'm going to present you the second place solution to the handheld device challenge. This work is done by Fan Huanhuan, Zhou Yuhao, Liang, Gao Shuang, Li Jingnan, and Guo Yandong from Oppo Research Institute. This figure illustrates our localization pipeline based on a standard retrieval-based framework. During offline preparation, a map of 3D point cloud is constructed with CoMap, and a semantic label is assigned to every point. During runtime, we extract feature points from the query image and predict the semantic segmentation and depth map with CNNs. We perform image retrieval and check the retrieval results with semantic and depth consistency. After that, feature matching and pose estimation is performed using geometric, semantic, and depth knowledge. We then cluster pose with dbScan and remove outliers of pose estimate. Finally, we combine all 2D to 3D matches and perform an overall weighted ransack with semantic information. Firstly, we propose a method for image retrieval verification using semantic and depth information. Our idea is to leverage semantic and depth skills to identify and remove bad retrieval results. Our work flow consists of 7 steps. Step 1, we perform image retrieval with stealth algorithm. Step 2, perform feature matching between every query and retrieval pair. In step 3, we count the proportion of matches with identical semantic label, producing a semantic score. In step 4, we also count the number of matches with low depth ordinal cost, producing a depth score. This will be discussed later. In step 5, we rank the retrieval result using semantic and depth score computed in the previous steps. In step 6, repeat step 2 to 5 and compute pose estimate for every query and retrieval pair. Finally, in step 7, cluster the pose estimate in step 6 and remove outliers. Our experiments show that superpoint and R2-D2 features have different spatial distribution. As shown in the figure here, superpoint on the left extract thick-like salient features, while R2-D2 on the right focuses on features with low repeatability. During offline map generation, we extract both features to produce a map of 3D points. And during runtime, we extract both features from query images and match against corresponding features in the retrieved images. Now, let's describe the use of depth prediction in visual localization. The depth map prediction is computed by a CNN using a single RGB image. We first verify the image retrieval results. The idea is to compare the depth of 3D points in camera coordinates with the predicted depth, assuming the pose is correct. In step 1, we compute the pose using 2D to 3D feature matches between the query image and a retrieved image. In step 2, we convert the 3D points to camera coordinate, take the Z value, and sort them in order. In step 3, we take the predicted depth values of the same XY locations, and again sort them in order. In step 4, compare the ordinal difference between the Z values and the predicted values. In step 5, the number of points with large ordinal difference is recorded as a measure of consistency of this retrieval result. We also leverage depth knowledge to verify feature matching results. The idea is to identify and remove matches with inconsistent depths. In step 1, we repeat step 1 to 4 in the previous section. In step 2, we remove matches with large ordinal difference. This slide shows a result on depth verification. The top figure is a depth map of a query image. The depth prediction network is trained with the MegaDepth dataset. We fine-tune the original model with data generated using the Aachen dataset. A bad and a good image retrieval results are shown in the bottom row, where red lines represent bad matches and the cyan lines represent good matches. In the left pair, though there are some feature correspondence, they are heavily occluded in the query image, which is behind the tree over here. This makes feature matching mechanism return a large number of incorrect matches, which is mostly identified with the proposed depth verification. The right figure shows a good retrieval result with similar number of inliers, where all the matches have passed the proposed depth verification. Here is the second result on depth verification for feature matching. The left figure shows the depth map. The right figure shows 4 inconsistent matches. 2 of them are identified correctly, which is the one here, and another one is here. However, due to error in single image depth prediction, there are 2 false positives. One is on the top edge of the building, which is the one here, and another one is at the edge of the window, which is the transparent material. To handle this problem, we compute reprojection error before and after removing inconsistent matches, and only remove ones which increase the error. We apply semantic knowledge in the process of ransack using the proposed weighted ransack scheme. The idea is that we adjust the ransack threshold with semantic consistency weight. We also compute the score of model hypothesis with semantic knowledge. Consider the first equation here. The semantic consistency weight is essentially an alpha mix between the total number of inliers and the number of consistent inliers. The weight is then normalized by being divided by the maximum weight amongst all the retrieved images by the second equation. The workflow of weighted ransack begins with computing the normalized semantic weight. In step 2, we randomly sample 5 matches and compute a model hypothesis. In step 3, the new inlier threshold is given by the first equation here, which is the original threshold multiplied by the normalized semantic weight. In step 4, the score of hypothesis for every other matches is calculated by the conditional equation shown here in the second equation. Detail is in the paper. In step 5, repeat step 3 to 5 for a number of iterations, and take the hypothesis with highest score. Here shows an experimental result, where a large view variation is observed. The top figure shows the matching result computed without semantic weight, where all matches are incorrect. The bottom figure shows matching result with semantic weight, where only one match shown on the right is wrong. Note that they cannot be identified, since both key points are labeled as building. In summary, Our work contains 4 main contributions. First, we re-rank the image retrieval results based on semantic and depth consistency. Second, we use multiple features to improve pose estimation. Third, we develop a new weighted ransack scheme using semantic weight. Our method has 3 major limitations. First, it will produce bad results at area where semantic segmentation or depth prediction is wrong. Second, it is highly time-consuming, which takes about 30 seconds per image on a regular PC. Third, it requires a lot of storage space for multi-descriptor 3D map and multiple CNN models. Thank you for your attention.
Thank you very much. We have time for 1 or 2 questions. So maybe I'll start. So one thing is you mentioned it's 30 seconds per image. Can you think of a way of making things faster?
Currently, we are using top 100 retrieval image. One thing I can think of is to reduce the number of retrieved image or use a better retrieval method. Thanks.
Thank you. Maybe one short second question. You mentioned for the semantic consistency that it's hard to get more information because a lot of things are labeled as building. Can you think of a way around that?
Yes, we also check the consistency using depth. If the depth is estimated properly, the false matchings on the building may be identified by the depth. Thanks.
Okay. And one final question. How is the Delph local feature in the retrieval part of the pipeline used?
Sorry, could you please repeat the question?
The question was just retracted. Never mind, I guess. Yes, thank you very much for the interesting talk.